Hi, my name is John Burden, and today I will be talking about our work, Latent Property State Abstraction. So, normal reinforcement learning systems can often suffer from a very high sample complexity, which can make the learning process very slow. We can alleviate this with domain knowledge of the environment that we're trying to learn in. This domain knowledge can be identified using abstractions of the environment and the solutions to those abstractions. Now, we usually use a human domain expert to identify these abstractions, and in our approach we opt to replace this with a method for an agent to learn its own abstractions using just experience with the environment. So, building on from the typical MDP formulation, we're going to use abstract Markov decision processes as well. These are essentially the same thing as MDPs, except we're just looking at a more abstract picture of the environment. They sort of capture the dynamics and environment as a whole at a much broader level. But functionally, they are MDPs themselves. So we're going to build our state abstractions, or our AMDPs and state abstractions around these, and we're going to focus on state abstractions, which means we're going to need a state abstraction function Z, which is going to map states from the original MDP to the AMDP, and we're then going to build the rest of the AMDP around this. We're also going to utilize reward shaping, which is a mechanism for encouraging desired behavior in an agent, and is basically revolves around giving the agent an additional reward based on good or encouraged behavior. Now, if we define the additional reward in a specific way, which is the difference of two potential functions of the states, then it's been shown that the optimal policy is guaranteed to remain unchanged. So the additional reward given is in the form seen here. Fs prime is gamma of the difference between the potentials. Now, we can use AMDPs for reward shaping. If we know the values for each abstract state, then using the potential function as the value function, then this has also been shown to give the sort of optimal potential function. We're going to do our experiments, and approach is going to be evaluated within OpenAI's car racing environment. We're going to slightly alter the action space in order to make it discrete, where the 20 actions correspond to different configurations of the accelerator, the brakes, and the steering. This just allows us to focus on some slightly simpler algorithms to improve while retaining the complex continuous state space. So we want to learn these sort of latent abstract state spaces. We're going to make use of variational autoencoders, which can learn to reconstruct pixel-based input or arbitrarily sized input through lower dimensional bottlenecks in the sort of typical autoencoder manner. Using this approach, we can take the original state space from a 96 by 96 by 3 full color pixel representation into a 128 dimension vector. And even though this is a drastic reduction in size, we can keep most of the information required to reproduce the image. Some samples can be seen here in the images going through the little diagram, where even though there is some blurring of the image, particularly around the red corner section, almost all of the relevant information has been retained. Now, this process for learning to do this with the autoencoder can be done automatically using random rollouts of the environment and doesn't require any domain knowledge, except for maybe the ideal size of the dimension of the size of the bottleneck. Now, we're now going to leverage the encoder portion of this network as a state abstraction function and form an abstract state space with this. So once this variational autoencoder has learned a reasonable reasonable weights, we can cut it down the middle and leave just the encoder part, and we can use this as our state abstraction function. We can form an AMDP using just this state abstraction function by retaining the original actions and interacting with the original environment, and then viewing the reward and transition functions through this abstract lens. As we see a transition S to S prime in the original environment, we can view this as the abstract function, or the abstract transition ZS to ZS prime. This AMDP has a much smaller state space than the original pixel-based environment, as the size of each state is much smaller. And interaction with this AMDP can be done in a model-free manner using the original environment. We can learn values, we can learn to associate abstract states to values, or abstract states and actions with values for reward shaping in order to improve the learning rate. So we can put all this together quite reasonably well. So we can put all of this together. We can take our car racing environment and we can learn the encoder. From there, we can learn using DQN, say, or any algorithm really, we can learn to associate pairs of abstract states and actions with abstract state values, and then use these for the reward shaping as outlined here. So in our experiments, we augment DQN with our reward shaping approach or our reward shaping based approach, and we evaluate the performance within our modified car racing domain. We compare our approach against both DQN, the purely abstract agent, as well as the world models. As you can see in the results here, our agent, which is in green, is performing, particularly in the early stages, much better than DQN. We also find that comparing against very different algorithms is difficult, as we see when we compare against world models, which performs much better in much fewer episodes. But when we look at a more sort of temporally based evaluation, our approach is indeed better. So it takes more episodes than world models, but takes less time to do to get to stronger performance. Within these results, we also don't show the pre-processing time, so we can focus purely on the shaping efficacy of our approach. So in conclusion, we can learn latent state spaces from using autoencoders and use these as abstract state spaces. So we can now completely automate the reward shaping process, and the learned reward shaping functions can be used to improve the performance of existing algorithms. Thank you for listening. I hope you'll check out the paper for a more thorough discussion of this work.